Right now, as you're watching this, a storm is organizing off the coast of Mexico that meteorologists expect to explosively strengthen within the next few days, potentially becoming the strongest hurricane the eastern Pacific has produced since last September's Hurricane Kiko. This is Hurricane Genevieve, and forecast models are showing it dropping to a central pressure of 963 millibars within just 4 days of forming. That number puts it on track to become the first major hurricane of this year's Eastern Pacific season, a milestone that hasn't yet been reached anywhere in this basin so far in 2026. At the exact same time, on the opposite side of the ocean basin, a separate system that meteorologists are describing as a monster circulation is developing in the Central Pacific. Long-range models suggest this system could become extremely long-lived and produce an enormous amount of accumulated storm energy over its lifespan. Today, we're going to break down exactly what's driving Genevieve's forecast intensification, why this specific stretch of ocean keeps producing storms capable of exploding in strength so quickly and so often, and what scientists are watching for as both of these systems develop simultaneously in the days ahead. If you want to stay ahead of this as the forecast updates over the coming days, subscribe and turn on notifications, because we track major storm development constantly. Let's get into it. Hurricane Genevieve formed off the coast of Mexico in the final days of July, in a region meteorologists have specifically flagged this week as highly conducive to rapid development. The storm is moving into an environment defined by low wind shear and unusually warm ocean water throughout. Critically, that warmth isn't just sitting at the surface. It extends well below the surface as well, providing the storm with a much deeper reservoir of thermal fuel than a system relying on shallow, easily disrupted surface warmth alone. According to the National Hurricane Center, Genevieve is forecast to become the first major hurricane of the 2026 Eastern Pacific hurricane season. Forecast models are showing the storm's central pressure dropping to somewhere near 963 millibars within just 4 days, a rate of pressure drop consistent with a storm undergoing genuine rapid intensification, rather than a slow, gradual strengthening process. By early in the week following its formation, forecasters expect Genevieve to reach Category 4 strength. That would make it the first storm of that intensity anywhere in the Pacific Basin since Hurricane Kiko struck in September of last year. To understand why forecasters are so confident about Genevieve's intensification forecast, it helps to walk through the 3 specific ingredients meteorologists look for when assessing a storm's potential to explosively strengthen, because all 3 are lining up simultaneously in this case. The first is wind shear, the difference in wind speed and direction at different altitudes in the atmosphere. High shear acts like a hand tilting a spinning top, disrupting a storm's vertical structure and preventing it from organizing efficiently. Low shear, which is exactly what's present in Genevieve's path right now, allows a storm's circulation to stack vertically and strengthen without that disruptive tilting force working against it. The second ingredient is sea surface temperature, which provides the raw thermal energy a tropical system converts into wind. The third, and the one that often gets overlooked in casual weather coverage, is ocean heat content at depth. Not just how warm the surface water is, but how far that warmth extends downward. A storm moving over water that's warm only in a thin surface layer can churn up cooler water from below as it moves, which naturally limits how strong it can become. A storm moving over water that stays warm well below the surface doesn't get that natural break applied and can continue drawing on that deeper heat reservoir, even as its own circulation mixes the upper ocean layers. Genevieve currently has all 3 of these ingredients working in its favor simultaneously, which is exactly why forecasters are calling for 1 or more distinct periods of rapid intensification as the storm tracks westward over the coming days. We've used this term throughout the video, so it's worth being precise about what it technically means because it's a formally defined threshold, not just a subjective description of a storm strengthening quickly. Meteorologists define rapid intensification as an increase in a tropical cyclone's maximum sustained winds of at least 35 miles per hour within a 24-hour period. Some storms exceed that baseline by such a wide margin that researchers track a separate, more extreme category specifically for cases where sustained winds increase by 58 miles per hour or more within the same 24-hour window. This isn't a rare, once-in-a-generation phenomenon anymore, and the underlying data on that specific point is genuinely striking once you look at it closely. Between 1980 and 2025, 190 separate Atlantic tropical cyclones underwent rapid intensification by this definition, and nearly a quarter of those, 46 storms, hit the more extreme threshold. In 2025 alone, 4 separate Atlantic hurricanes, Erin, Gabrielle, Humberto, and Melissa, all underwent rapid intensification. Remarkably, every single one of those 4 storms reached the extreme rapid intensification threshold rather than just the baseline definition. Research increasingly points to warmer oceans, driven by broader ocean warming trends, as a contributing factor behind this apparent increase in how often storms are hitting these rapid strengthening thresholds, since warmer water provides more of the raw thermal fuel that powers this kind of explosive development in the first place. This year's Western Pacific season already gave us a vivid, real-world demonstration of exactly how extreme this process can get. In early July, Typhoon Baby intensified by 75 miles per hour in a single 24-hour period, and by 100 miles per hour across 36 hours, both figures dramatically exceeding the official rapid intensification threshold by a wide margin. Baby went on to become the third storm to reach Category 5 equivalent strength anywhere on the planet in 2026, following Tropical Cyclone Horatio in the southern Indian Ocean in February and Super Typhoon Sinlaku. Sinlaku struck the northern Mariana Islands in April with winds reaching 185 miles per hour, killing 17 people and causing an estimated $1.5 billion in damage. Genevieve's current forecast trajectory places it on a very similar track to what we watched unfold with Bavi just a few weeks ago, organizing quickly, encountering close to ideal conditions, and being flagged well in advance for the potential to explosively strengthen. While Genevieve dominates the immediate forecast conversation, meteorologists tracking the broader Pacific Basin have flagged something else developing simultaneously that's worth understanding, because it illustrates just how active this particular stretch of ocean has become this year. Forecasters describing recent model output have specifically called out what one meteorologist termed a monster circulation, developing in the Central Pacific. A system current model guidance suggests could become unusually long-lived. Storm longevity matters for a specific technical reason worth explaining. Meteorologists track a metric called accumulated cyclone energy, or ACE, which measures not just how strong a storm becomes at its peak, but how long it sustains that strength over its entire lifespan. A storm that reaches a powerful peak intensity but dissipates quickly contributes comparatively little to a season's total ACE. A storm that reaches a strong, sustained intensity and maintains it over many days contributes dramatically more, even if its peak winds never quite match a shorter-lived, more explosive system. When forecasters flag a system as likely to be exceptionally long-lasting, as they are currently doing with this developing Central Pacific circulation, that's specifically a signal about its expected contribution to the season's overall energy total, a genuinely different kind of concern than a single sharp intensity peak. Separately, in the Western Pacific, another system, Typhoon Newell, is also being tracked, with forecasters suggesting it could reach somewhere in the range of 85 to 90 knots, just short of major typhoon intensity. They've flagged an outside chance of its own burst of rapid intensification within the next day or so. Taken together, Genevieve in the Eastern Pacific, the long-lived circulation developing in the Central Pacific, and Newell in the Western Pacific represent three separate, simultaneously active systems, a genuinely busy stretch for global tropical activity, even by the standards of an already active 2026 season. This isn't happening in isolation from the rest of this year's global tropical activity, and it's worth stepping back to see the full pattern. Before Genevieve even formed, 2026 had already produced three separate Category 5 equivalent tropical cyclones on three different ocean basins. Tropical Cyclone Horatio in the southern Indian Ocean in February, Super Typhoon Sinlaku in the Western Pacific in April, and Super Typhoon Bavi, also in the Western Pacific, in early July. That's a remarkable clustering of the absolute most extreme storm category across multiple geographically separate ocean basins within a single calendar year. Meanwhile, the Atlantic Basin, which usually draws the most media attention during hurricane season given its direct impact on the United States, has been comparatively quiet this year, with forecasters describing it as being on an extended holiday vacation through much of July, with little expected through at least the middle of the month. That's an important, easily overlooked detail. A quiet Atlantic season does not mean a quiet global tropical season. The atmospheric and oceanic conditions driving explosive storm development this year have been concentrated heavily in the Pacific, both the eastern and western basins, rather than spread evenly across the globe. This is exactly why storms like Bavi, Sinlaku, and now Genevieve have generated so much attention despite occurring far from the Atlantic coastlines most Americans associate with hurricane season coverage. There's a specific scientific concept worth understanding here, because it explains why forecasters can confidently predict how strong a storm like Genevieve is likely to get, even before it happens. Meteorologists use a framework called maximum potential intensity, pioneered by MIT hurricane scientist Carrie Emanuel, which calculates the theoretical maximum strength a tropical cyclone could achieve given the specific atmospheric and oceanic conditions present in its path. Critically, Emanuel's research demonstrated that human-caused warming is gradually raising this theoretical ceiling over time. This means the absolute strongest a hurricane or typhoon can physically become, under perfect conditions, is higher today than it would have been decades ago. It's genuinely rare for a real storm to actually reach its full theoretical maximum potential intensity. Achieving that ceiling requires a nearly perfect alignment of conditions, since the atmosphere and ocean form an extraordinarily complex system where that level of perfection is achieved only occasionally. Bobby, for example, was approaching a calculated maximum potential intensity of roughly 200 miles per hour with a central pressure of 880 millibars in early July. But an eyewall replacement cycle, a natural process where a storm's inner eyewall collapses and gets replaced by an outer one, interrupted that intensification before Bobby could reach its theoretical ceiling. Whether Genevieve encounters a similar interruption or continues on an uninterrupted path toward its own maximum potential intensity is precisely the kind of detail forecasters will be watching closely over the coming days. Since eyewall replacement cycles came up in explaining why Bobby fell short of its theoretical ceiling, it's worth explaining this process in more detail. This is one of the more important and more genuinely unpredictable factors that will determine how strong Genevieve actually ends up becoming, regardless of how favorable the surrounding conditions look on paper. As an intense tropical cyclone strengthens its original eyewall, the ring of intense thunderstorms surrounding the calm central eye can become so tight and so intense that it starts to choke off its own inflow of warm, moist air. Around that same time, a new, larger ring of thunderstorms often begins forming further out from the center, effectively competing with the original eyewall for the same supply of atmospheric fuel. When that outer ring wins that competition, the original inner eyewall collapses and dissipates, while the outer ring contracts inward to become the storm's new primary eyewall. During this transition, a storm's peak winds typically weaken somewhat, since the new, larger eyewall is initially less efficient at concentrating the storm's energy than the tighter eyewall it's replacing. Once that new eyewall fully contracts and organizes, the storm can resume intensifying, sometimes reaching an even higher peak intensity than it achieved before the cycle began. The timing and outcome of any individual eyewall replacement cycle remains one of the more genuinely difficult aspects of hurricane intensity to forecast precisely, even with modern satellite and modeling tools. This is exactly why experienced meteorologists tend to frame intensity forecasts, including the one currently pointing toward Genevieve reaching Category 4 strength, with appropriate hedging language rather than absolute certainty. The broader atmospheric and oceanic conditions can be about as favorable as they get, and a storm can still fall short of, or occasionally exceed, initial forecast expectations, depending on exactly how and when its internal eyewall structure evolves over the following days. It's worth spending a moment on why storms like Genevieve get taken so seriously beyond just their peak wind speed numbers, since wind alone doesn't capture the full scope of what a major hurricane or typhoon actually does to the coastline it eventually reaches. Storm surge, the abnormal rise of ocean water pushed ashore by a storm's winds and low pressure, is responsible for a substantial share of hurricane-related fatalities historically, often exceeding the death toll directly attributable to wind damage itself. A storm's surge potential depends on a combination of factors beyond just its peak wind speed, including its physical size, its forward speed as it approaches the coast, and the specific shape of the coastline and ocean floor it's approaching. This is why two storms with similar peak wind speeds can produce dramatically different surge heights depending on exactly where and how they make landfall. Wave height is another factor worth understanding, since it's directly relevant to the kind of intense systems we've been discussing throughout this video. During Bobby's peak intensity phase in early July, significant wave heights of up to 39 feet were reported in the open ocean surrounding the storm, waves generated entirely by the storm's own powerful, sustained winds acting on the ocean surface over a large area. Waves of that scale pose serious hazards to any shipping traffic in a storm's path, and they contribute directly to the kind of coastal erosion and infrastructure damage that continues well after a storm's peak winds have already passed. Rainfall represents the third major hazard category, and it's often the most dangerous one for inland communities specifically, since a weakening tropical system can still produce catastrophic, slow-moving rainfall totals long after its wind field has diminished to a fraction of its peak intensity. This is a pattern responsible for some of the deadliest tropical cyclone impacts in recent memory, even from storms that never reached major hurricane strength at their peak. For residents along the eastern Pacific coastline of Mexico, and for anyone in Hawaii monitoring the broader tropical picture given how active this basin has become, the practical guidance here is the same foundational preparedness that applies to any major storm season. Know your evacuation zone if you live in a coastal area. Have several days of emergency supplies, water, food, medications, and a way to charge essential devices without grid power. Monitor official forecasts directly from the National Hurricane Center or Joint Typhoon Warning Center, rather than relying solely on secondhand social media summaries, since track and intensity forecasts can shift meaningfully as new data comes in over a 24 to 48 hour window. And take rapid intensification forecasts seriously even when a storm's current. Observed strength doesn't yet look particularly threatening, since the entire point of a rapid intensification warning is that conditions can transform a moderate storm into a dangerous major hurricane within a single day. A storm currently sitting well below major hurricane strength is forecast, with real confidence grounded in genuine meteorological science, to become one of the most powerful storms on the planet within a matter of days. That's not sensationalism. It's the direct, predictable output of three specific atmospheric and oceanic ingredients: low wind shear, warm surface water, and deep ocean heat content, all aligning at the same time over the same patch of ocean Genevieve happens to be tracking through right now. None of this guarantees Genevieve will actually reach the full intensity current forecasts suggest. As we've covered, eyewall replacement cycles, shifts in ocean heat content along the storm's exact path, and other genuinely unpredictable factors could all interrupt that trajectory in either direction, weakening the storm below forecast expectations, or, in rarer cases, allowing it to exceed them. What forecasters can say with real confidence is that the underlying environment is about as favorable for rapid strengthening as this basin produces, and that alone is enough to justify the kind of close, sustained attention meteorologists are giving this storm right now. This year has already given us 3 separate Category 5 equivalent storms across 3 different ocean basins. The pattern driving that activity shows no clear sign of slowing down as we move deeper into the most active stretch of the global tropical season. We'll keep tracking Genevieve's forecast track and intensity closely, along with the other active systems developing across the Pacific right now, updating this coverage as new advisories come in. Subscribe so you don't miss any of it. Drop a comment and tell me if you're anywhere near the eastern Pacific coastline or in Hawaii, watching this storm activity yourself, and which of these 3 active systems, Genevieve, Newell, or the developing Central Pacific Circulation, concerns you the most. I read every one of these. Stay safe out there, and I'll see you in the next one.